Okay, everybody, this is for our Geometry AB for 5th hour class. These are going to be our notes on section 10.4. And if you guys remember, the quiz we took on Friday covered 10.1, 10.2, 10.3, then we jumped and did 10.5. And I told you guys we'd come back to 10.4, and sure enough, here we are. So 10.4 deals with the concept here of perimeters and areas of similar figures. And if you remember from back in the day, when we talked about this at the beginning of chapter 7, which we did in December, similar figures are going to be any two polygons that are the same basic shape but different sizes. So for an example over here, if I were to draw a pentagon that looks something like that, and then I were to clone that figure right next to it, these two polygons right now are congruent. They're exactly the same size and exactly the same shape. But if I shrink one of them down just a little bit or made it larger, now these two polygons are said to be similar. They're the same size, but different shapes. The two important concepts we talked about in two figures like this that are similar is that all of their corresponding angles were going to have to be congruent. So if this was a 108-degree angle in this pentagon, you've got a 108-degree angle in this pentagon as well. But the other thing, and probably what's more important for what we're doing here today, is that the ratio of their corresponding sides were all going to be proportional. So just for the sake of argument, if this side right over here had a length of, let's say, 12, and this one right over here would be half of that, let's say 6, then we could go over here to this side, and if this side was 10, this side right over here would be half of that one, which would be 5. So that's just a quick little recap about similar figures. And as we look at it here today in Theorem 10.7, everybody, part 1, we're going to break this down into 2. Here's what this theorem says. If two figures are similar, then the ratio of their perimeters is the same as the ratio of their corresponding sides. And that's this equation right down here in the box, that the ratio of the perimeter of the first figure to the perimeter of the second figure is equal to the ratio of the side from the first figure to a corresponding side in the second figure. We also called this ratio right here, everybody, that one right there, we called that our scale factor back in the day, the ratio of two corresponding sides. So that might be something that we have to revisit there in a little bit moving forward. Okay, anyhow, let me undo that. All right, and let's see what that kind of looks like in action. So what I did right here is I just made two really simple rectangles. And what I think you'll see in looking at them pretty quickly is that they're essentially the same shape. This rectangle is a 2 by 3 rectangle. 2 if we measured the squares down the left-hand side, and then 3 if we went to the bottom. And for this bigger one over here, you'll notice I just doubled everything. This one is 4 rectangles going down the side, and then 6 going along the way right over here. So if we were going to write something like a ratio right here of a side, oh, that shouldn't be happening, sorry guys, like a side, give me a second everybody, let me see if I can fix that. Okay, we're back. I just found that I can't use my finger to draw on my screen without it doing something weird like that, so we'll have to make do. Anyway, back to this particular rectangle here on the left. What we can see here, guys, is that it has right here, I guess what we call a height of 2, whereas this rectangle over here had a height of 4. And then this first one on the left right here would have a base of 3, and this one on the right here would have a base of 6. And we're not going to do this very often, but I just thought it would be easy if we went ahead and made these simple squares here so that we could realize that as we looked at this first figure right here, this side, which we'd call side number 1 over here, is going to have a length of 2. Okay, whereas over here, a corresponding side in the second figure, we'll call that side 2, was going to have a length of 4. So I was trying to make this one easy to see here that this one on the right is going to be twice as big as the one over here on the left. If I call this maybe base 1 over here on the left and said that that had a length of 3, we could do the same thing over here and say that the second base, so we'll call that base 2, was going to have a length of 6. Now, the nice thing about this and the big takeaway here as it relates to that theorem that we just talked about is if we set up the ratio right here that we just saw on the last slide, perimeter 1 to perimeter 2 should equal the same ratio as side 1 to side 2. Let's try that. In fact, maybe we can copy that. And let's put it right down here in this figure and see what it looks like. Now again, with everything being squares here, this should be pretty nice and easy for us just to count. The perimeter of this shape right over here looks like we're going 2, 3, 4, 5, 6, 7, 8, 9, 10. So the perimeter of the first object here is going to be 10. And if we make a fraction there and look at the perimeter of the second one, we're going to find that that perimeter is 4, plus another 6 makes 10, plus another 4 is 14, and another 6 there is going to make 20. So the ratio of our perimeters right there of the two similar figures is 10 to 20. And that should equal the same as the ratio of the corresponding side. So if I look at the heights, the side in the first figure was 2, and in the second figure was 4. So a ratio of 2 to 4 right here. And if we recall from back in chapter 7, there's a couple of things we could do to verify this. The first one right here may be to cross multiply, to take the 10 and multiply it by the 4, and then take the 20 and multiply it by the 2. And if we were to do that, I think we would see that the 10 times 4 is going to get us 40 for our first cross product. And then that's going to equal, here we go, the 20 times the 2, which is also going to be 40 for our second cross product. So that kind of verifies that theorem right there, everybody, that says that the ratio of two perimeters is the same as the ratio of the corresponding sides. The second part of that theorem deals with areas now, not with perimeters. And because area is a two-dimensional measurement, this theorem gets a little bit more complicated. This one says that if two figures are similar, the ratio of their areas is equal to the ratio of the squares of their corresponding sides. So here, in parentheses, we're taking the ratio of side 1 to side 2, and we're squaring that entire ratio here, which we need because area is two-dimensional. It's square units. So looking at those exact same two figures right here, we can figure out areas real quickly just by simply counting up squares because these are relatively small diagrams. And if we were to count the area here, 1, 2, 3, 4, 5, 6 square units is what we get for the area of that figure. Whereas over here, if we started counting, there's 1, 2, 3, 4 rows, and 1, 2, 3, 4, 5, 6 columns. So that's going to tell us now that the area of that second figure is going to be equal to 4 times 6. That was going to be 24 square units. Now this is important to realize because what we said a moment ago right here is if we were measuring just side lengths right here, the side in the first figure, if we were just counting the height, for example, would be 2 units. Whereas over here, a side length in the second figure was going to be, that one was going to be 4 units. So what we saw a moment ago with sides and with perimeters, the second figure was twice as big as the first. But here as we look at areas, we can see that the area of the second figure, which is 24, is actually 4 times the area of the first. So let's go back and let's steal that formula here that we wrote down just a second ago. We'll copy that, paste that right over here, and then move it out of the way. And let's see if this actually works out now, everybody. So in this case right here, area of the first figure we found right here was 6. So in this location right over here, I'm now going to replace that with a 6. Over, here we go. Area of the second figure comes from right over here, which was 24 units. So that fraction right there, that ratio of 6 to 24, should equal, and here we go now, everybody, the ratio of the corresponding sides squared. Okay, so our first side length, or just a side in the first polygon, we said was 2. That's going to go right here. For S2, a corresponding side length in the second polygon was going to be 4. And this is the most important thing here, everybody. That 2 right there. When we're talking areas, we have to square the ratio of those sides. Okay, so to figure out what's actually happening right now, let's take a look here. A couple ways we could go with this right here. That 6 over 24 could be simplified here. In fact, let's go ahead and do that. We can divide a 6 out from both of those. All right, and dividing out a 6, 6 divided by 6 is going to be a 1. 24 divided by 6 is going to be a 4. And now when we go to simplify the ratio on the right, a couple of ways to do it right here. Remember that when you're squaring a fraction, everybody, that exponent kind of gets distributed to both the numerator and to the denominator right there. So this 2 squared in the numerator is going to get us 4, and the 4 squared in the denominator is going to get us a 16. Now you could cross multiply here if you wanted to, but I was hoping you guys would see at this point right here that the first fraction is already simplified as a 1 over a 4, and the second fraction of 4 over 16, when you divide out a 4, also simplifies to a 1 over 4, and that kind of verifies what we're talking about right there. Okay, so let's see some of that stuff then and some examples moving forward. I thought rather than trying to cook up a bunch of new examples, what we would do is actually take a look at the real homework assignment that you guys are going to be doing on this section. Now, this says lesson 11.3 because it comes from the old textbook, but as I posted on our classroom page, this document right here, guys, that says Geometry AB in the e-learning plan, okay, this is the 10.4 worksheet for this section. All right, so this is what we're going to be working on. And I assigned just the odds, everybody, because I thought we would do the evens here together as we go through some of this to kind of help you out. So we're going to get started on just a couple of problems here together, and we'll see how long this takes. So let's take a look at number 2. You'll notice in this one right here, guys, they gave you the ratio of the perimeters, which was right here at 3 to 5. And we're supposed to come up with the ratio of the corresponding side lengths and the ratio of the areas. So if we want to know the ratio of side lengths, let's go back a couple of slides here, everybody, to where it said that the ratio of your two corresponding side lengths right here is exactly equal to the ratio of the perimeters. They are one and the same. So if the ratio of our perimeters is 3 to 5, the ratio of our corresponding side lengths has to be exactly the same of 3 to 5. Now when we look over here for ratio of areas, let's go back 2 slides right here and look at this idea, that the ratio of the two areas is the square of the ratio of their sides. So what that means is if the ratio of our side lengths is 3 to 5, the ratio of the areas is just the square of these two numbers. The 3 squared is going to get us a 9, and the 5 squared to the right of it then is going to get us a 25. Ooh, so the ratio of our areas then, everybody, is going to be 9 to 25. So the first two columns are going to be the same, ratio of side lengths and ratio of perimeters, and the ratio of the areas is just the square of those two numbers. All right, let's take a look at what's going on here in number 4. They tell us here that these two polygons are similar, and we're supposed to find the ratio of the perimeters and the ratio of the areas and find the unknown areas. So what we see here is a side length of 2 in the small figure, 4 in the big figure, and an area of 3 square feet in the first figure, and we've got to come up with a couple of things here. Okay, so we're supposed to come up with the ratio of the perimeters and the ratio of the areas. So on number 4 here, guys, we wrote down that, you know what, rather than do that, let me go steal this again here, that the ratio of our corresponding perimeters was the same as the ratio of our side lengths. So back to this problem here, let's shrink this guy down, and we'll put this right here. Ratio of the perimeters is the same as the ratio of the side lengths. And so the ratio of our side lengths here, everybody, in the first figure, there was a side length of 2 feet. And in the second figure, there was a side length of 8. And of course, anytime we can, we would want to simplify that fraction, and that ratio of 2 to 8 is going to get us a ratio of 1 to 4. So that right there, everybody, is the ratio of your perimeters. They also wanted us to find the ratio of the areas. So to do that, we need the more complicated formula, which is located right here. So let me copy that, and we'll put this one down right underneath it here and see what we can do for number 4 here as well. So to do that, the ratio of your areas is the square of the ratio of your sides. So let's try this again now. Side 1, just like before, is still going to be 2. Side 2, just like before, is going to be 8. But now, since we're talking areas here and it's two-dimensional measurements, we have to remember to square that ratio right there. So we're going to square this mess. And if you guys just wanted to put this in your calculator in one step, that would be fine. The 2 over 8, when you square it, becomes a 4 over 64. Simplify that ratio, and you're going to end up with a 1 over 16 for the ratio of your corresponding areas. So the ratio of the areas here would be 1 to 16, whereas the ratio of your perimeters here was 1 to 4. Okay, and that's really the way you're going to do 5 and 6 and 7 as you're running through those. Like we've been talking about all chapter, the best thing you guys can do is write down a formula and then fill in what you know after that. All right, let's move on to number 8 here. Directions here tell us that the ratio of the areas of two similar figures is given, and we want the ratio of the lengths of the corresponding sides. So once again, we're going to use this same formula right here, guys, that relates the ratio of areas to the ratio of corresponding sides. So that would really be step 1 there. Okay, write down the formula that kind of guides us through all of that, and that's the following. Step 2, we said, fill in what you know. All right, so what do we know here? In this problem, they gave you the ratio of the areas, and that's exactly what's going on right here. So our area 1 looks like it's going to be 9, and underneath that, area 2 is going to be 25. Okay, and that's going to be equal to, and normally now, with 4 variables in this problem, we'd really like to know one of these and to be able to solve for the other. They didn't give us either one of those, so I've got to leave both of these unknown right here as side 1 over side 2, close your parenthesis, and square all of that. And as I said, it looks like there's 2 unknowns, but if we look at the directions, they really just want the ratio of the lengths of corresponding sides. They want this fraction right here by itself, and the only thing we have to get rid of is this 2 or this square here. So something we haven't done a whole lot of this year, although we did it in the Pythagorean theorem a little bit, and you'll see it more next year. To get rid of a square, we're going to do a square root on both sides. So we'll do a big square root on the right, and we'll do a big square root on the left of the entire fraction. Okay, and then step 3, solve that equation and come up with what we need to do right here. So what's going on? The square and the square root right here cancel out. So we just end up with, and I'm going to switch sides on you guys here, the ratio of side 1 over side 2. And that's exactly what we were being asked to find right here, is equal to, and then we look over here on the left, and lucky for us, 9 and 25 are both perfect squares, although you'll notice that really in just about every one of these problems. So it works out nicely. When we take the square root of 9, we get a 3. And when we take the square root of 25, we get a 5 down underneath that. And that right there, everybody, is exactly what they asked us to find in this problem. Find the ratio of the lengths of corresponding sides, and we got it right here at 3 to 5. Okay, moving right along right here. Whoop, too far. Okay, so let's take a look at number 12 and see what's going on here. So in this problem, use the given area to find xy, just the length of this side right over here. And I think we would probably like this better if we put a variable up there. So since they're already using an x, I'm going to draw a really bad n, all right, and we'll run with that. Now in this problem, again, they've given us some side lengths here, but they've also given us areas. So like we always do, step 1 is going to be to write down the formula here, and it's going to be the same formula that we've been using right here, the one that relates areas with corresponding sides. Okay, so that right there is going to be step one. Step two, right underneath that, fill in what you know. Okay, I'm looking first for area number one, which means the area of the first figure. And right here they told us that the area of the first figure is 25 square centimeters. Underneath that, we're looking for A2, the area of the second figure, which is right there at 225. Okay, and that's going to equal, here we go now, in parentheses, side 1 over side 2 quantity squared. So side 1 means a side length in the first figure, which they've given us right here as 6 centimeters. So that's going to go there. And the corresponding side length in the second figure would be right over here. And that's what we're trying to find, the measure of xy here, which we've just gone ahead and labeled as an n. And again, the one thing that's really easy to forget when you're doing area problems, that square is the most important thing. So that's going to go right there. Now, there's a couple of different ways you could proceed from here. My preference would be that since we're trying to solve for n, the square is the last thing happening on the right side, so it's the first thing that we're going to undo. We're going to do a square root on the right and balance that out by doing a square root on the left. Okay, so on to step 3 now, although I think this is going to be a 2-step process at least. Let's do a square root. You guys can use your calculators here if you need to take the square root of these numbers right here, but hopefully we recognize a couple of these. The square root of 25 is 5, and the square root of 225 is 15. But the 5 over 15 is going to simplify further to a 1 over 3. And again, if you did that all in your calculator, it would tell you that in one step. Over here on the right, the square and the square root cancel. And so what we have on the left, the 1/3, is just equal to a 6 over an n. Okay. And now to go on further from here, this one's pretty simple. In some cases it might be a little bit more complicated, but this is a proportion here, so you could cross multiply. But in this case it works out nicely. The 1 times n just gives you an n, and the 3 times 6 is going to get you an 18 now for the measure of that missing side. And that right there, everybody, is what we were looking for the answer to this problem here, that n is equal to 18. Now what that basically tells you, if we go back up here, if this side was an 18, the figure on the right has a side length that's 3 times as big as the figure on the left. 18 is 6 times 3. But the area then isn't 3 times as much. The area is actually 9 times bigger. We took the 3 from the scale factor and squared that to get 9, and sure enough, 25 times 9 is equal to 225. So hopefully we can kind of see what's going on there with that. Okay, a couple of always, sometimes, never problems, which we don't do a whole lot of, but let's just run through the couple of evens right here, and I'll let you guys worry about the odds. Number 14, two squares with the same perimeter are blank similar, and we're supposed to write either always or sometimes or never. Well, for two squares to have the same figure or the same perimeter, that basically tells you that they're going to need to be exactly the same figure right here. For them to have the same perimeter, just get that guy, there you go. If we duplicate that right there, the only way two squares can have the same perimeter is if they're congruent figures. And congruent is a little bit funny, but technically if two figures are congruent, it does match the definition of them being similar. It means that they're the same shape and their side lengths are proportional as well. So this one right here for number 14 is actually going to be always. Let's take a look at number 16 then. Okay, number 16 right here. Two right triangles with the same area are blank similar. Again, always, sometimes, or never. Okay, and to figure that one out, we've got to think about what it could look like. Two right triangles with the same area. Well, we kind of have the same thing going on right here in 16 that we had in 14 to an extent. This is going to look really bad if I try to draw it. But if I wanted to make two right triangles that looked something like this, Okay, and a right triangle would have to have a right angle here like that. So if there's one of them right there, if another right triangle was going to have the same area, the first question we should probably ask is, could they be similar? Oops. And if we wanted the figures to be the same, I could clone that and move this one right here. In this case, yeah, these two figures would be similar and they would have exactly the same area. But just for the sake of argument, let's just say here that in this first triangle here, it had a base of, let me go with 6 and a height of 4. And if we did this, everybody, then the area of that triangle right over there would be 1/2 times its base times its height. 6 times 4 would be 24, and half of that would be 12 square units. The question then becomes, is it possible to draw another figure that's got the same area that isn't similar to that one? So what I'm looking for is just another base and height here that would have the same product as the base and height in the first figure. So here's a really badly drawn right triangle as well. And this time, you'll notice I made it a little bit shorter. What if we made the height here 3, but I tried to make it a little bit longer? What if the base was now 8? And in this case, the area of this triangle would again be 1/2 times base times height. 8 times 3 is going to be 24 as well, and half of that is still going to be 12. So here are two figures right here with the same area, both 12 with the same dimensions of 4 and 6, that are similar. But if I look at this triangle and this triangle over here, they've got the same area and they're not similar. So anytime you can make this happen, where the statement can be true or it could also be false, that's going to be a sometimes for problem number 16. Okay. And a couple of word problems at the end, and then we're just about done with this one. So let's take a look at number 18 here, guys. It says the ratio of the areas of two similar triangles is 16 to 9. They want the ratio of the lengths of corresponding sides. So yet again, it's another problem with this same formula here of A1 over A2 is equal to S1 over S2 quantity squared. And let's fill in what we know here, guys. We've got the ratio of the areas right here at 16 to 9. So area 1 would be 16. Area 2 would be 9. And that would equal, here we go. And again, they're asking you here for the ratio of the lengths of corresponding sides. So they're not telling you either one of these numbers. So that just remains a side 1 over a side 2. Sorry, and then we're going to square all of that. So once more, they're not looking for us to solve for a side, they just want that ratio. We're going to get rid of this square by doing the square root of the right and balancing it out with the square root of the left, and we're just about done. The square and the square root cancel, so we're going to get side 1 over side 2 equals, and we take the square root of 16 over the square root of 9, and that's going to get us a 4 over 3. And that is all they were asking us for in this problem, the ratio of the corresponding sides. So that's going to be 4 over 3 for that answer. I think I want to take the time to do number 20 with you guys here as well, because that one's a little bit different than the one that we just did. So let's take a look at this guy. Ratio of the lengths of corresponding sides in two similar rectangles is 3 to 5. And again, we're dealing with area. So yet again, everybody, it's the same formula here. A1 over A2 equals side 1 over side 2 squared. And now let's fill in what we know. Okay, what do we have? The ratio of the lengths of corresponding sides is 3 to 5. So what's over here on the right in parentheses, the ratio of sides is going to be a 3 to 5. So that goes here. Close off the parenthesis. Don't forget to square that. What else are they telling us here in number 20? The smaller rectangle has an area of 36. Now, since 3 is smaller than 5, we know that the figure number 1 that we're talking about on the top is the smaller one, and they tell us that its area is 36 square inches. We do not know the area of the second figure, so we're going to call that one just as A2. Sorry, guys, I thought I was recording there and apparently I had stopped. Okay, so I think we left off problem number 20 somewhere around here, where we set up the area of the first figure here to be 36. The area of the second figure was unknown, that was A2, and then the sides over there on the first figure was a 3, the second figure was a 5, and that ratio was getting squared. We distributed the square to both parts right there and got a 36 over A2 is equal to a 9 over 25. Cross multiplied and got 9 times A2, which was just 9A2, and the 36 times the 25, I did that on my calculator over there and got 900, so that's where this came from. And then from there, the last thing we had to do to solve for A2 was to divide both sides by 9. The 9's canceled. 900 divided by 9 got us 100. So the area of the second figure here was 100. Okay, everybody, that pretty much wraps up what we're going to do for 10.4. So I'd like you guys to try the odd problems on that assignment. Remember that if you have a printer at home and you want to print out that worksheet, that's great. But if not, just take out a blank piece of paper and just kind of, show your work on there the way you would normally do with an online assignment. And you guys can just take a picture of that and turn that in to me. Okay, email me if you have any questions. Good luck, everybody.